Hello, everyone. Thank you for attending this talk. It's a pleasure being in Code Blue, and it's a pleasure being in Tokyo. It's my first time in Japan. And I'm here to talk to you today about a recent research project that we did. We named it What the FAX. So just before we begin, a bit about ourselves. So this is me. My name is Yaniv Balmas, and I'm a security researcher. I work for Checkpoint. And my colleague in this research project is Eyal Itkin, also security researcher at Checkpoint, which unfortunately could not be here with us today. But he is with us in spirit. So before we begin, just a bit about the history of FAX. So it all began in 1846 when a scientist named Alexander Bain invented the first ever something that looks like fax machine. He sent the first image of a wire. This happened in 1846, just roughly 20 years before the invention of the light bulb, right? And then it continued in 1860. The first thing that looks like a fax machine came to be, again, 20 years before the invention of the telephone. And then there were more developments like radio fax. And then in 1966, a very small company that nobody heard of called Xerox, they came out with the first commercial fax machine. It looked like this. And then in 1980, a group called ITU defined the current standards for fax, namely T30, T4, and T6. So apparently, fax had a very big part in the technological history. And it really changed the way that we send and receive electronic documents from one to the other. But that was all in the past. I mean, today we have far better ways to send electronic documents from one to the other, right? So let's just try and compare fax to one of the more common techniques. Let's say email, for example. So just to remind you, we are comparing this to this, right? So in terms of quality, I really have nothing to add. You just saw the pictures. In terms of accessibility, well, I'm pretty sure that most of you, if not all of you, have 24/7 access to emails. Not so sure you are carrying around your fax machines with you. In terms of reliability, well, when you send an email, you know that it gets received or not received. But when you're sending a fax, you have absolutely no verification. Yes, there is this page saying received okay, but if there was no paper in the printer, for example, you still get the same receipt. So absolutely no reliability in fax. And regarding authenticity, well, we can argue whether or not email is authenticated, but there are solutions like public key cryptography and stuff like that. What we don't have is we have nothing for fax. Absolutely nothing, right? So looking at this table, you might think, okay, so nobody should use fax anymore, right? Well, wrong. Everybody uses fax. It's used in naval, in ships, in the open seas to receive this kind of very critical topology maps. In Japan, fax is very popular. Almost everybody in Japan uses fax. And if you just do some Google combos like, contact us and fax, you will find something like 380 million results on Google. So these are the published fax numbers on Google. Think about how many fax numbers are not published. It's simply huge, right? And thinking about that, it's not only the numbers, it's not only how many people are using fax, but it's also who is using fax. Well, if you're a small company, a medium company, or a huge corporate, you use fax. You have a fax number, right? I don't know if you receive anything over that fax number, but you do have a fax number. If you're a Bank of China, it's the biggest bank in the world, and this is their fax number. We just Google it up. And obviously, if you're a government institution, you really love fax. You wake up in the morning and you want to have some fax. So if you want to fax Donald Trump in the White House, this is the fax number. Again, just Googled it. So fax is out there. And I think that the crazy thing is that sometimes these government institutions, they don't only allow you to send fax, but it's actually mandatory to send fax. There is no other way. You cannot send an email. It's either postal mail or fax. This seemed like a crazy thing to us. I mean, we are in 2018. How can it be that we are still so dependent on fax? So in order to understand that a bit, you need to understand how does fax looks like today. You see, 20 years ago, fax was this standalone machines, right? It was only fax, but today, fax, the same old technology, is wrapped with newer technologies. So, for example, we have, services like email to fax, fax to email, stuff like that. We have fax over radio, we have fax over satellite, and I think that most commonly, we have these things. It's all-in-one printers. These things come shipped with a telephone cord that you can connect, and they do fax. They do a lot of other things, but they also do fax. It's default. And our research, in our research, we decided to focus exactly on those all-in-one printers. So if you look at these printers from a security point of view, you can consider them to be black boxes, right? And on one side of these black boxes, you have interfaces like, Wi-Fi, Ethernet, Bluetooth, stuff like that. Those interfaces connects the printer basically to the internal network, to the external network, or to the world. And on the other side of this printer, there's this little interface which connects it to, well, somewhere in 1970, I would say, to the telephone line. And so if you understand that at the end of the day, those printers are really nothing but computers. I mean, they have CPUs, they have memories, they have an operating system. So we thought to ourselves, okay, what will happen if an attacker sitting somewhere in the world with access to the telephone line and equipped with its target's fax number, what will happen if he will be able to send a malicious fax that will enable him to exploit this printer and actually take control of the printer? If he would be able to do that, he could then pivot through any one of the other interfaces, let's say the Ethernet, and go into the internal network, effectively creating a connection between the external world and the internal network through nothing but the telephone line. It's 1980 again, right? So we thought that this is a really cool idea, and challenge accepted. And we decided to do it. So after we got a bit excited about all this thing, we sat down and actually started thinking about the challenges ahead. And it turns out that there are quite a few challenges. And let me just name the major ones of them. So, for example, okay, how do we obtain the firmware? How do we obtain the code of this printer? And then how do we analyze this firmware? And then what operating system is this thing running? Is it Windows? Is it Linux? Is it a real-time operating system? I don't know. And after we understand that, how can we debug this thing? Debug a printer? I never debugged a printer. And then after we understood all this, we need to understand how does fax even work? I don't know. And after we did all that, we can start discussing where can we find vulnerabilities inside this printer. So these are a lot of questions. And today, during this talk, I'm going to take you through all of these questions one by one. Hopefully, you will understand everything by the time that I'm finished. So let's start with the first question. How to obtain the firmware of the printer? So we had to choose a printer to work on and meet our printer. This is the very poor printer that we abused for so long. It's an HP printer. It's an HP OfficeJet printer. We chose HP not because we dislike HP, simply because HP has something like 40% of the market share for printers. So they seemed like a very good target to us. And this specific model, well, I can say a lot of things about why we chose this model, but basically, it's the cheapest one. So yes, we bought this printer, and now we need to break fax. But before we break fax, we need to break the printer. And I mean literally, break the printer. So this was the fun part of the research. So we took everything apart, and it looks something like this. Basically, this is the heart of the printer. That's how it looks like from the inside. So it has a lot of components on it. Let's try and look at them. So this is a flash ROM manufactured by Spansion, and this is an SRAM. So if you look at it, it might look like two little components on this PCB, and that's right, because it has another side. And on the other side are the more interesting components, stuff like USB, Wi-Fi, electricity, SRAM, this big battery that does something, I don't know. But most interesting, there are two components here. One of them is this, and this is the main CPU. It's a CPU manufactured by Marvell, and it's manufactured proprietary for HP. So you can't get this online. You can do nothing with it. It's just It's just for HP. And then there is this. This is the FAX modem. And what we need to do in our research is to understand these two components and the relationship between them. If we can do that, maybe we can do our work. So, as I said, the first challenge was to obtain the firmware. And when we look a bit closer at this PCB, we find some things that look very promising. Two interfaces, one of them is called serial debug, another called JTAG, and it's clearly marked on the PCB. So looking at this, if you're not familiar with these interfaces, so basically they are debugging interfaces. They will let you read memory, write memory. So basically, this is what we need in order to get the code of this firmware. So when we looked at this, we say, this is going to be too easy. But unfortunately, things don't go the way we want to every time. JTAG is completely disabled. We cannot use it. And the serial port, we were able to connect to it, and we got this nice terminal, which gives us this error for almost every instruction that we try to do. Error, I don't understand. Well, we don't understand either. But what we do understand is that the serial is not going to get us very far. So we need to find some other way to get this firmware. Luckily for us, after looking a bit, we find a very nice FTP site online. So this is the FTP site. Apparently, it's an HP FTP site which contains every firmware version for every HP product ever produced in the entire history. It's a huge FTP site. It actually took us something like 2 weeks to find our firmware inside this mess of firmwares. It was very funny. But then we found the file. And now that we have the firmware update file, which is supposed to contain the code for the firmware, we now need to understand how do we upgrade the printer firmware. I never did it before, and I have no idea how to do it with this file. So we need to understand it. And the answer to this question is surprisingly funny. How do you upgrade the printer firmware? Yeah, you just print it, of course. It turns out that this printer has this listening port that receives print jobs. This is defined by an HP document called PCL XL Feature Reference Protocol Class 2.1 Supplement, that if you are still sane after reading all these things, you understand that the printer accepts a firmware upgrade just the same way as it receives a print job. That's it. And looking at our file, it really correlates with that because, you see, it says PJL, print job language. This is exactly what we expected to see. So now that we understand this, we need to somehow open this file so we can read it. It's compressed somehow. And after reading this PCL document, we kind of understand that this thing is composed of a lot of encoders. So we need to decode them one by one. I'm not going to go through all of the decoder because, you know, it's quite boring. But just to give you the overview of it, it contains stuff that's called null decoder, TIFF decoder, delta row decoder. They are all decoders. They do something like, if the previous line was all spaces, then if the next line is also all spaces, just write 1 instead of the line. It makes sense when you're talking about a print job, you know, when a print page. But when you're talking about a firmware, a binary file, it makes absolutely no sense. But still, this is what it uses. And we left about this and said that, you know, when you're a hammer, everything looks like a nail. And when it turns out that when you're a printer, everything looks like a print job, including the firmware. So, okay, we managed to decode everything. And now we have something that looks like a valid file. And now we need to understand how to analyze it. So we start to look at this file. And right in the beginning of this file, we see something that looks like a table. So we define it, and we understand that it really is a table. And this is a table that actually defines sections. You see, it says something like loading address, section name, and location in binary. So this is great, because now we understand that this big file that we are looking at is just composed of smaller sections in it. And this table actually defines each and every section, so we can now break this into the respective sections and look at every section. And that's exactly what we do. And then we find one section that looks really interesting to us. It's actually the biggest section, and it really looks like what we're looking for. We are looking for the code for the printer, and this is what we see. Take a look. It says, error, I don't understand, right? So it's exactly the same thing that we saw on the serial. So probably, yes, this is our code. This is what we were looking for. But if you look closely, it's not exactly there. We are almost there because some characters are missing from this thing. So it's not complete. And those characters are consistently missing from the entire file. So although we know that we are there, until we will know what these bytes are, we can't really go on. So we really need to understand what they are. So the question is, what is this? Why are those bytes missing? Probably it's another compression algorithm. Well, we have no idea why you need another compression. It makes no sense, but it's actually the least craziest option, that it's another compression algorithm. So we decide to go with this way. Also, if we try to compress this thing with something like zlib, one of the most standard compression algorithms, we get 80% better compression. And we know that the printer has zlib in it because we can see the strings for zlib. So why didn't they use zlib? I don't know. But the problem is still there, and we need to handle it. So now we need to understand those missing bytes. And let me walk you through the analysis process of this. So this is one of the code snippets that I just showed you, and let's try to decompress this thing together. So if you look at this thing, basically it's composed of two main categories. One is ASCII characters, stuff that we can read, right? And the other is non-ASCII characters, stuff that we can't read, right? And look at this, at the byte view. And let's take out the ASCII characters. And we are left only with the non-ASCII characters. Now, these are actually our missing bytes. This is what we can't read. This was replaced with something else. We need to understand what was it replaced with. And now, if you stare at this long enough, you will start seeing a pattern. And let me make it a bit clearer to you. You see, it's composed of, again, two types of missing bytes. One is 1 byte and 2 bytes and double bytes. And the distance between the 1 bytes looks suspiciously patternish, I would say. 8 bytes, 9 bytes, 9 bytes, 9 bytes, 8 bytes. And this starts looking like a pattern. I mean, and if you look at this from a different perspective, maybe the pattern will start being a bit clearer. You see, the FF and the FF, they look the same. The F7 and the F7, they look the same, but what does it mean? And in order to understand this, you need to sharpen your binary view a bit. And if you understand that FF stands for 8 1 bits, and if you do this consistently for everything, then now you see your pattern. You see, the 0 bit always falls within this 2-byte hole, always. And it's consistent throughout the entire page, so the entire file. So that's great, because now we understand that the first byte is simply a bitmap. It's defining the next 8 bytes. Wherever there was a replacement, there will be a 0 bit. That's it. So great. We understand what is this 1 byte. But now we need to understand what are those 2 bytes. That's a big question. And if you know anything about compression, then you know that there's not a lot of options here. It could either be something like a forward or backward pointer, or it could be a dictionary, an index to a dictionary, or it could be something called a sliding window. Well, we can pretty easily say that it's not a forward or backward pointer, and also we can say that it's not a dictionary, simply because, you know, if we try to reference it, we can't find what we are looking for, so we rule these options out. So it must be a sliding window. And when we have this information, we go to our favorite place, to Google, to try to find something similar, and we run into in some dark corner of the internet this nice site explaining something called the soft disk library format. It defines a lot of things, but inside this there is a compression algorithm that looks similar to ours. Actually, it looks really like ours. Actually, it looks exactly like ours, exactly. And we found it very funny because this thing was invented around 30 years ago and used in history in one place. Can you guess what place was this? No, it wasn't HP at all. It was in Commander Keen. Yes, this is the compression algorithm designed and used in Commander Keen, the game that I grew up playing. So we found this really funny. But now that we understand this, we can actually understand what these 2 bytes are. So basically, what they are, they just define a window location and data length, which is all the information that we need in order to decompress this thing. Let me explain to you how this works. So we have an input text, an output text, and a sliding window, right? And let's try to decode this string here, okay, using this method. So the first byte is a bitmap. We don't know what the value will be, so we leave it open for now. And we begin. So A, we write it both in the output text and in the sliding window. Then B, the same, C, D, and then when we hit A is already present in the sliding window, so we don't need to write it in the output text, and then B is just the following character, so again, we don't need to write it. And then E is a new character, so what we write here is 0002. What it means is go to the sliding window at position 0 and take the first 2 bytes, right? And then you continue, E, F, G. That's all there is to it. Now you know the bitmap, there was a replacement here, and you know the value here, and that's it. That's how you decode this thing. It looks very easy when you look at it that way, right? But looking at it reverse is, I think, a bit more problematic. So that's great. Now we can open this file, and now we actually have a firmware code that we can look at. And now we need to understand what operating system and what is this code even. And this took us quite some time, but let me just give you the brief explanation of it. So we are looking at an operating system, a real-time operating system called ThreadX. The CPU it's running on is ARM9, it's big Indian, and it's manufactured by a company called Green Hills, which is manufacturing stuff for missiles and airplanes for the US military, so it's pretty good real-time operating system. And then it's composed of several components like system and stuff, common libraries, and tasks. Tasks are the rough equivalent of processes in normal operating systems. And in system, we have a 2-stage bootloader and some networking framework and stuff like that. And then common libraries, just common libraries that we all know and use. And tasks, yeah, we can define this task and we see them. And after we have this picture here, so now we know that we need to concentrate on these tasks. Nothing else is important. These tasks are the tasks that control the FAX functionality. So if we look at them, we might be able to find vulnerabilities in there. But just a second before we do that, we see something that looks pretty suspicious here. And this is SpiderMonkey. I don't know if you're familiar with SpiderMonkey or what it is. SpiderMonkey is the JavaScript implementation of Mozilla. And we were thinking to ourselves, why would the printer need to implement JavaScript? Well, it's not a web browser. There's absolutely no logic for it to use JavaScript. And we found this question pretty intriguing. So we started looking up where is it used in the printer. And it turns out that the question is pretty simple. It's used in a feature called PAC, P-A-C. PAC stands for Proxy Auto Configuration. It's something that configures your proxy automatically when you connect to the network. And the most important thing here is that the top layer of this functionality was written by HP. And when we're looking at this top layer functionality, we see something that looks like this. Look at this. So it turns out that before doing the proxy auto configuration, the printer connects to this URL, fake URL 1234.com. It just connects to it. It does nothing with that connection, just connects to it. Maybe some kind of sanity testing. I don't really know why, but it does do that. And the interesting thing here is, do you know who owns this domain, fake URL 1234.com? Any guesses? It's not HP. You're right. I do. It wasn't registered. So I registered it for $5, and now every HP printer in the world connects to my domain. Hey, that's very nice. And if HP is listening, I'm willing to sell this domain for a very good price. Please contact me. So yes, that's it. And now, after we talked about all this, we can finally talk about FAX. So T30. T30, also known as the ITU-T recommendation, T30, is the de facto protocol for sending fax over phone line. It's actually does all the heavy lifting. All the fax functionality is in this T30 protocol. And if you have a fax machine, it is using T30. There is no other option for it. It was designed in 1985, and it was last updated in 2005. Yeah, 30 years ago. So we started looking at this protocol, and it was very hard to analyze because it has graphs like this. It might look like maybe doable, but every one of these nodes has another state machine in it and another state machine in it, and it was really, really, really very, very messy. And there's a lot of dynamic tables and dynamic tables and dynamic tables, and really looking at this statically was not going to get us anywhere. We weren't going to go anywhere. So what we need is basically we need a debugger. We need some way to debug this printer. And the question is, how can you debug a printer? Well, it's a good question because you see we have a lot of challenges. How do we debug this? There's absolutely no native way to debug the printer. There are no debugging facilities. We have no control over the execution flow. We can't stop the machine. We can't go and we can't actually do anything. And even if we could do something with it, there's a hardware watchdog. Hardware watchdog is just watching the CPU, and if the CPU halts, he will just restart the printer. And basically what a debugger does when you put a breakpoint, it puts you in an endless loop, basically halting the CPU. So even if we could put a breakpoint, the hardware watchdog will just throw us away and restart the printer, so we go nowhere. So we need to find some way to overcome this. And you know, every research project and everything in life needs a little bit of luck, and this is where our luck came to be. And roughly at the same time we did this, a company called Senrio found a vulnerability called Devil's Ivy. It's a vulnerability in the GSOAP open source library, and luckily for us, the printer has exactly this version of GSOAP, so we have a vulnerability in our printer, and we can actually exploit it using its web interface. So that's great. So now we can exploit the printer, so we have control over the execution flow. But just to show you how it looks like, this is the vulnerable part in the printer that containing Devil's Ivy. If you don't spot the vulnerability, it's okay. It's here. Basically, the vulnerability is an integer underflow. So what this means, I don't know if you're familiar with data rates for sending fax, for printers, sorry, but this means that we need to send over 2 gigabytes of data in order to exploit this vulnerability. And each one of these iterations takes us around 7 minutes. So we have to exploit this thing, start working on it, and then, you know, we crash something, and then we have to wait for another 7 minutes, and another 7 minutes, and another. So we waited a lot of 7 minutes during this research, and it looked something, I think, like this. A lot of coffees. Do this, go get coffee. Do this, go get coffee. So it was fun. Okay, so we need to find some way to debug this thing. We need to find some way to basically read and write memory. Now that we have control over the execution flow, we need to load our own code, and we need to somehow bypass memory protection on the printer, and somehow embed the debugging stub into the current firmware. What we did is design our own debugger. We called it Scout. It supports x86, x64, ARM, on both ARM and thumb mode. We used it before to debug Linux kernel, and we can also use it in an embedded mode. In this mode, it's very versatile, so if you have any firmware research that you are doing, you can basically take this thing, define the functions, if you know their locations, and boom, you have a debugger. And if you want this tool, you can go ahead and get it here. We have it on our GitHub account. I think you will find it pretty useful if you're doing anything like this. So yes, now we can actually debug this thing. And now, after we did all this, we need to understand how does FAX even work. So again, let me give you the brief explanation of it. A fax there's a sending fax, sending modem, a receiving modem. There's the CPU that does all the heavy lifting, and then there is all the print jobs and stuff to do printing. So we start with the first stage. At the first stage, there are several phases. A phase called network interaction, probing, arranging, equalizer and echo canceller, and a training phase. If you don't know these phases, it's okay, but basically you all know them because they sound like this. So that's the beeping sounds that we hear when we send fax. All they do, basically, at the end of the day, is create a tunnel between the receiving and the sending modem, a tunnel called an HDSC tunnel. And over this tunnel, all the other protocols work. So basically now, the modem and the CPU are using T30 protocol. And T30 protocol is also divided into several stages. In phase A, we have a caller ID saying, hello, I'm this thing. And then in phase B, we're doing some kind of handshake, like I have these features, you have these features, let's decide that we are using these features. Yeah, pretty standard. And then on phase C, we actually send the data. And then on phase D, we say, okay, thank you, goodbye. Basically, this is T30 in a nutshell. So let me show you when you send a fax, how does it work? So a normal fax, a black and white fax, is sent as a TIFF file over this entire thing that I showed you, over the HDLC tunnel, and then over the data section in phase C, and then it gets to the printer itself. And basically what you send is the TIFF body. Now the printer needs to have a TIFF header in order to print this thing, and the TIFF header is composed of the data that is sent in phase A and phase B. So now we have a complete TIFF file, and it goes to printing, because this is what you do with fax, you print it. So that's nice. But now it turns out that T30 has a lot of extensions to it. And some of these extensions are really, really weird, I think. One of them is called the color extension. Yeah, it turns out that you can send colorful fax. Did you know that? I didn't know that, and I actually have no idea why should you send a colorful fax, but apparently you can, and it's supported on almost every printer. It's almost default in it. The procedure is pretty much the same procedure. The only difference is that now, instead of sending a TIFF file, we are sending a JPEG file. And also, it's not just a JPEG, it's a full JPEG file. So we are sending both the header and the body of the JPEG file, and then again, it gets received by the printer and then printed. So yes, that's very nice. And now we can start talking about where we can find vulnerabilities. So you saw all of these layers of sending a fax. Basically, we could look at any one of these layers in order to find vulnerabilities. But we decided, because it's most convenient, to start looking at the topmost layers. And specifically, we wanted to look at the JPEG parsing, because we're sending a full JPEG file, so maybe we have more control of the user data, and maybe we can find vulnerabilities there. So before we discuss the vulnerabilities, let me explain to you how a JPEG file looks like. Basically, this is kind of a JPEG file. It's composed of sections, like a start of image, app, and then it has a size and data, and then another section with its size and data, and then another section with its data, and then another section which is the end of image. This is how basically a JPEG file looks like. And now let's try to look at one of these sections. Specifically, it's a compression section. Again, compression is a repeating motto in our research. So this section defines a compression table. It looks like this. It has a header, it has a size, it has a 4x4 matrix, and then it has data, right? This is how this section looks like. And the way it works is that you basically take this 4x4 matrix, and then you sum up all the values. And you see, if you sum up all the values here, you will get the value 6. It's 1 and 2 and 1 and 2. And then you take 6 bytes from the data section, right, because this is the sum, and you copy them into a 256 stack buffer, right? Look at this for a second. Do you see anything strange here? Well, if you're dealing with vulnerability research, you probably already understand the problem here, and let me explain it to you. What will happen if I will send here all FFs? What will happen is that the printer will think that he needs to take roughly 4K of data from the data and copy this 4K into a 256 bytes long stack buffer. So this will create an overflow. This is just as simple as that. So basically, we have a stack overflow, a very primitive and very nice stack overflow. We have absolutely no constraints because we can send any data. We have no forbidden bytes. We have around 4K of controlled data that we can send, and the file even contains more information that we can use later in our exploit chain. So this is great. So we have an exploit now for the printer over fax. And now that we have it, we need to bypass all the OS mitigations that the printer provides. Just kidding. There is no, there are absolutely no protections on this operating system. So basically, once you have a Stack Overflow, you basically control the printer. So these are the two CVEs that we received from HP for the vulnerabilities. HP defined them as critical with a CVSS score of 9.8, which is pretty rare for any vulnerability. And this is HP's response. I must read it. When HP learned of this issue, they worked quickly to provide updates to mitigate risks. HP takes security seriously and encourages customers to keep their systems updated to protect against potential vulnerabilities. Basically, this vulnerability affects all HP OfficeJet printers. So that's around 100 different models of HP. And it gives you full control of the printer. So let me show you a short demo of how this looks like. So this is our attacker machine. It connects to a modem that we bought in Amazon for $5. We run the script, and we send our malicious fax. And this is our printer. So now the fax gets received. Oh, as you can see, it's sent from an evil attacker. We found it funny. And yes, basically, we have complete control over the printer. But this is not enough, because we want to show how we can go from the printer to any computer connected to it. So what we did is put eternal blue inside of our fax that we sent. And now every computer connected to the printer will immediately get exploited, as you can see here right now. So it's a cal popping. That means that we can do anything we want on the computer. Basically, we did exactly what we planned to do. So we showed how we can get into the internal network just through using malicious fax. So that's pretty much it. So some conclusions. PSTN, Public Service Telephone Line, is still a valid attack surface even in 2018. Fax can be used as a gateway for internal networks, and all the outdated protocols are pretty bad for you. So try and not use them if you can. But what can you do to protect yourself against this thing? Basically, one thing you can do is patch your printers. If you have an HP OfficeJet printer, this link here, provided by HP, will tell you if your model is vulnerable. If it's an OfficeJet, it is vulnerable, and you can download the updates. We actually flew to HP headquarters to help them create the patch for this, and the patch works, I can tell you. Another recommendation is, if you don't need fax, don't connect it. If you buy this printer, don't just connect it to the fax if you don't need it. You better leave it alone. But if you do need to connect a fax, maybe the best thing to do is to segregate your printers and have them on a separate VLAN or something like this. So if somebody can take control over the printer, at least it won't be able to propagate to the rest of the network. And though these are all very good recommendations, maybe the best recommendation I can give you here today is, please, stop using fax. It's 2018. It's time that we evolve into newer ways of sending documents from one to the other. And I can't finish this talk without giving some credits to friends who helped us a lot during this research. So these are them. They deserve the credit. They helped us physically, technically, mentally, and however you would like to say. And special thanks to Yaniv, which made it all happen. And that's it. You can find more of our work here if you want to see. Thank you very much.